So hi, today I'm gonna discuss about top-down dynamic programming approach, which I did not discuss in my previous video. So let's get started. So first of all, what is top-down dynamic programming? So let's have a look. Suppose we have a problem, which is problem 1, problem n. So what recursion does? It simply calls the problem for a smaller input, again for some smaller input, and finally it reaches at some initial state where we can directly get the solution, which means the base case of the recursion, and by the returning time we can solve the another problem. So basically this is the thing which is also true for top-down problem. Top-down problem states that from for a larger input uh, call another problem which is similar in nature for the smaller input, and by solving the smaller problems we obtain our solution. So let me drop this. And there is another one approach which is called bottom-up approach. So this is that if we have the initial solution, that means for the base case of the recursion, from this solution we obtain the solution for a larger input, and again and again we obtain our actual problem solution. So this flow is called bottom up, and this flow we have to reach first the base case, and then we can solve our problem. This is called the top-down approach. So let me discuss it with our example, which I want to explain. So here is the example. We discussed it earlier how the recursion works, and it takes order of 2 to the power n time for this solution. So I didn't discuss this, which is the dynamic programming solution. So how does it works? So first of all, dynamic programming uses memory. So here from this code you see what is the memory. Yes, the TP array, which is the global array, is the memory. So how it will help to obtain our solution? So let me discuss about this. So first of all, this is the array, so we have to initialize it somewhere, and we all know for initialization we have memset function which takes 3 arguments, and this is the value by which we want to initialize our array. So we initialize our array by -1. So suppose here n equal to 5, so it comes here, it checks the base conditions, and here after here, so here it is the new line, is n equals 0 or n equal 1. This is the same thing. we have to return 1 from here. Here we have another line which is dp of n is not equal -1, so we have to return dp of n. So why this line? Let me explain. So, and also here you see that when we call the pivot d of n-1 plus pivot d of n-2, we have another line which is dp of n. So what we do here, before return, here we directly return this Fibonacci of n-1 plus Fibonacci of n-2. We store it in our dp table. So initially we have all the elements here as -1. So if we store this value in the dp table, that means it doesn't contain here -1. So if it will check here that if it is not -1, so we directly return. So for this we did not call this function again, which saves for some overlapping subproblems. So let me explain it. So go to the whiteboard. I already made a diagram for this. Okay. So here I have called f of 5, and for f of 5 I have f of 3, and here I have f of 4. For f of 3 I have f of 1 and f of 2, and so on. So let me explain the flow, how our recursion solves this problem. So from f of 5 it comes here f of 3 first, and then from f of 3 it goes to f of 1. So since here f of 1, which is for n equals 1, we have to return 1 here. And initially you consider I have the dp array initialized with -1. So here I have returned 1. So is f3 completed its execution? No. From f3 it checks for f1, then it comes to f2. So for f2 I have 2 calls. So first it obtained from f0, which will return 1 here, and from f of 1 we have written 1 here. So it is true for the recursion calls also, but here one catch is I have 1 and 1. So if I add this to 1 plus 1, 2, before return it from this function I stored it in our dp table. So that is dp of, sorry for the bad handwriting, dp of 2 equal to 2. I store it here. Okay. So when it comes to, so now f2 returns dp of 2. So when it comes here, from this to here, we have 2 here also. So if I add those 2, we have 3. But here we also store this value in our dp table. dp of 3 equals 3. Initially we all have -1 in this case, but here before return from this function I store it here. It will help in our future work. So let's see how it can be helpful. So here F3 returns F5 is dp of 3. That means 3. It will return to f of 5. So now f of 5, our call comes to f of 4. So from f of 4 I got two calls. One is f of 2, another one is f of 3. Here now here is this is the utility of this dp table. Here it checks first if I have already calculated the value for f of 2 or f of 2 or f of 3. Yes, I have already calculated it. I have already calculated the value for f of 2 and f of 3 here. So what it will be returned, it does not execute further, it does not execute its branches, it directly returns here, which is dp of 2. Sorry. That means 2, and it will also return dp of 3. That means 3. And now we have to add this here and also store it in f of 4. So f of 4 becomes dp of 4 equals 2 plus 3, that is 5. So f of 4 returns 5 here. So if we obtain f of 5, we have 3 plus 5, that means 8, which is the fifth Fibonacci number. Sorry. Which is the 8th Fibonacci number. 5th Fibonacci number, sorry. So here you see that if here I have already calculated the value for f of 2 and f of 3, and for this we have saved here these calls, that is f of 0, f of 1. We don't need to extend the branches for, and for f of 3 I have also f of 1 and f of 3, sorry, f of 2, and again we have f of 0 and f of 1. So these extra branches will come if I don't store the value in our dp table. So suppose this here we have n equals 5. What if we have n equals some large value, suppose 1000? So if I don't store this value in our dp table, it will become huge amount of extra calls. So this is the advantage of dynamic programming, and that's how the top-down dynamic programming works. So that's all for today. So thank you guys, keep watching, bye bye.